We now continue with our review of classical mechanics by looking at the Poisson bracket formulation of dynamics. Poisson brackets will give us insight into some of the Lie algebra structures that we will encounter later. The Poisson brackets are defined by the following equations. The Poisson bracket of two variables, u and v, which are functions of the generalized coordinates q and p, of which there are n coordinates q and n coordinates of generalized momenta p, are defined as the sum of the partial derivatives of u with respect to qi, v with respect to pi, minus the partial of u with respect to pi, and you can see that this is reversed, partial of v with respect to qi. Obviously, therefore, this is an antisymmetric form, and the bracket of uv is the negative of the bracket of vu because of this sign right here. The summation over I occurs over all generalized coordinates, and there must be, as you recall, exactly one generalized coordinate q for every generalized momentum p in the Hamiltonian formulation. And it can be shown that the values of all Poisson brackets are independent of the set of canonical coordinates in which they are expressed. In other words, if we go to another set of canonical coordinates, and you recall that canonical coordinates are a set of coordinates for both the coordinates and the generalized coordinates and the generalized momenta for which Hamilton's equations hold, then we can always express these in terms of Poisson brackets. Looking at the Poisson brackets, we can see that the partial of any that the bracket of any function f with some coordinate qi is equal to minus partial of f with respect to pi, and f with respect to pi is partial of f with respect to qi. How does that arise? Well, f with respect to qi from this equation right here means that we have the partial of we're going to have the v is going to be a q, and so we have a partial of q with respect to p, and so that vanishes. So the first term vanishes. Then the second term is the partial of a q with respect to q, which gives us a delta ij, a minus sign, which means that the u, which is now the function f, is replaced right here, is taken the partial with respect to p with respect to I, only for the I that is associated with this coordinate q. Therefore, we have just proved that the bracket of f with qi is minus partial of f with respect to pi. Likewise, by the same substitution, if we put f and p in for u and v, f and p, the first term will work, but the second term will be a partial of p with respect to q, which vanishes, because all the coordinates and all the momenta are functionally independent. Therefore, we just end up with the first term, which is partial of f with respect to q, and a partial of p with respect to p, which gives us a 1 for that one qi, and therefore we end up with a partial of f with respect to qi. If we were to let the function f be the Hamiltonian h, and let the capital p's and q's be small p's and q's, we can see that we would get a bracket of qi with h, which is partial of h with respect to pi. Now, partial of h with respect to pi is going to be equal to qi dot, according to Hamilton's equations. Likewise, over here, we can see that the bracket of pi with h is minus partial of h with respect to qi from this function right here, which is equal to pi dot. Therefore, it follows that the bracket of any q with h gives us q dot, any p with h gives us p dot. More generally, therefore, it follows that the derivative of any function with respect to time is the bracket of that function with respect to h, which gives us its time derivative, plus the partial of u with respect to t. Now, in order to arrive at that result, we had to use Hamilton's equations here and in here in order to get the time derivatives. Thus we can conclude that for functions that do not contain the time explicitly, and thus for which the partial of the function with respect to t vanishes, these are constants of the motion if u and h have Poisson brackets that vanish. Again, let me repeat that. If we have a function u which does not contain the time explicitly, and if the Poisson bracket of that function with the Hamiltonian vanishes, we find that its time derivative vanishes, therefore it's a constant of the motion, or equivalently, we say that it's a conserved quantity. We can see, therefore, that the Hamiltonian is the generator of a time displacement. Likewise, we can also show that the angular momentum function right here is a generator for the time for the rotational motion. P is a generator for translational motion, and in general, this is a precursor to what we will learn with Lie groups and Lie algebras, that these brackets with the various Lie algebra components, and there we will have commutator brackets between operators rather than Poisson brackets, which are derivatives, functional derivatives, we will get exactly the same results, namely that the angular momentum generates an infinitesimal change or derivative with respect to theta in that direction. The Hamiltonian generates an infinitesimal derivative with respect to time. Therefore, there's an extremely close connection between the Lie algebra formulation and the commutator that we use there and the infinitesimal transformations that they generate and the Poisson bracket expression that we have used right here. Let's look at some other information that pertains to the Poisson brackets. The first thing that we want to discuss, in addition to its antisymmetry, which we just discussed, is the fact that it obeys an equation called Jacobi's identity. This is very simple for the student to, and straightforward for the student to prove this. The Jacobi identity can be written in the following way, and it holds for all Poisson brackets in any variables. The Jacobi identity between three functions, u, v, and w, is the bracket of u with the bracket of v and w, and thereafter a cyclic permutation of u, v, and w over its three cyclic permutations. So we first write u, v, w, then u, v, and w over here, then u, and then v, w like this. The sum of those three brackets always vanish. That will hold with commutators between matrices. In other words, it will obtain when we have Lie algebras, and it also obtains for all generalized coordinates for Poisson brackets. Now, an interesting result is that we can make a deeper connection in the Jacobi with the Poisson brackets and define actually something that we could call a differential operator. We can define the operator d sub v by the following definition. It's the partial of v with respect to qi, partial with respect to pi, minus partial of v with respect to pi, partial with respect to qi. We notice that this differential operator is exactly as though we had pulled the function u out of the Poisson bracket and left the Poisson bracket as a differential operator that acts on the function u, as we have written here. So we can see explicitly that the Poisson bracket of any functions v and u is a differential operator defined in terms of the function v acting upon another function u. This kind of gives us a basis for what we will learn later in the connections between differential equations and Lie groups, Lie algebras, and Poisson brackets. This deeper connection with Lie algebras and groups will be explored later in the course, but generally a function g can be used to generate a canonical transformation in another function by an infinitesimal amount, delta f, by using the following expression. If we take the bracket of f and g, multiply it by an infinitesimal change d lambda, that will give us an infinitesimal change delta f. Let me repeat that again. we can generally take a function g, which we use to generate a canonical transformation in another function. So one function can generate a canonical transformation in another function, and do that infinitesimally by an amount delta f by the following equation. Now, if we think about what that means, it means we could take any function that we use in classical mechanics and use something like the Hamiltonian to generate how it would change in time, or the angular momentum to generate how it would change under a rotation, or the momenta p to understand how it would change under a translation. So, for example, g might be angular momentum, and in that case the delta lambda would be delta theta, and delta f would be the change in that function under the rotation. In closing out our discussion of classical mechanics and our very brief and quick review, I want to very quickly go back and review some information on work and potential energy before we go forward. Everyone who is taking this course is fully aware that work is defined as the infinitesimal work is the force dotted with the infinitesimal displacement as the dot product of two vectors, thus leaving the work as a scalar as a result of being the product of two vectors. In fact, if we think of the infinitesimal work as being a perfect differential, we can write it as the negative of a differential minus dv, if it's a perfect differential, where dv is written as the partial of v with respect to x dx plus the partial of v with respect to y dy plus the partial of v with respect to z dz. That already one can see that from that f is equal to the negative of partial of v with respect to the associated coordinate, and that gives the force in that direction. We also recall for kinetic energy that the force is the mass times the acceleration, or the time derivative of the velocity. Thus, as we do in introductory physics, we can write the change in the work as m dv dt dx. Then we can take the dt, put it under the dx, and write that as the velocity. So we now get the infinitesimal change in the work as mass times velocity times change in velocity. If we perform the integral of that to get the total amount of work, and we're going to integrate between a velocity of 0 up to a velocity v, that will give us the amount of work it is required in order to take an object from rest and move it upward to a velocity v. That total amount of work to get something going at velocity v from rest is this integral, which is 1/2 mv squared, as evaluated between those two limits. That is the work necessary to move the mass from rest up to the velocity v, and so we write the kinetic energy, k is equal to 1/2 mv squared, to represent the energy of motion, or kinetic energy. Likewise, we can talk about the potential energy. And the potential energy in a gravitational field is written as mgh with a force which is equal to mg, is obviously the change in work is force times distance, which we can integrate and get mgh if we take it between a height of 0 and a height of h. The potential energy for a 1/r squared field can be found in a similar way with which everyone is familiar. If our force is alpha over r squared, then the potential energy will be the integral from, say, some reference point r naught up to r of alpha over r squared in the radial direction of a unit vector, or unit radial vector, dotted with dr. Now, of course, this is a radial vector pointing away from the origin that's a unit vector dotted with dr itself, and so the dot product of these is just the magnitude dr. We bring alpha, a constant, outside of the integral sign, and then this becomes r to the minus 2 dr. When we integrate that, we realize that the integral is simply 1/r with a negative sign. It's very easy to check that. Just take r to the minus 1 and take its differential. The minus 1 cancels here, and we get 1/r to the minus 2. So we have the negative of alpha times 1/r evaluated between r and r naught. When we write that out, it's it's minus alpha divided by r plus, at the other end of the limit, alpha over r naught. It is convenient to take r naught, our reference point for all of these forces that are 1 over r type of potentials, to be 0 at infinity. So we reference our point at infinity. And the reason for that is, obviously, if we were to reference the point 0, this would explode and we would be adding infinity to everything. So we take r naught to be infinity, and that gives this term vanishing. And so we can write the potential energy as minus alpha over r. In the particular cases of the gravitational potential energy, this gives us minus capital G m1 m2 over r. And for the potential energy in electrostatics, we get K times Q1 Q2 over r. Finally, it's very simple and straightforward for the student to show that if our force was minus K times X, a Hooke's law force for a system that's near equilibrium, the potential energy there is 1/2 kx squared, which is easy to show even though that's not a radial force, except for the symmetric isotropic three-dimensional oscillator. Reviewing very quickly the electrostatic force for the electromagnetic field, if we think of two charges, Q1 and Q2, then we know that the force between those, the Coulomb force, acts across the vacuum with nothing intervening. And we get a force, at least in magnitude, which is Q1 times Q2 over r squared times the constant K, which did not show up there. This is a very interesting situation because it seems counterintuitive. It seems counterintuitive that a force could reach across a distance here with absolutely nothing but a vacuum in between, and one particle could exert a force on another. And so there was a conjecture that rather than just reaching across the vacuum with a force, and now we're going to write that force exactly, force 1 on 2 is minus K Q1 Q2 divided by the difference between the position vectors squared and a unit vector that goes r1 minus r2 over the magnitude of r1 minus r2. We're going to conjecture that this force arises from a field. And what do we mean by a field? That issues from a charge Q1 where Q2 finds itself in that field and therefore experiences the force. Well, this seems like just a trick to mathematically make us feel better. What we do is we take the charge Q2 and we pull it out of that equation and factor it out front and write the rest of the material, the rest of the factors as simply an E1. So all we've done is factor the equation into Q2 and everything else. And therefore E1, the electric field generated by the charge Q1, is given by this equation, where this should be a 1 right here. And this is minus K Q1 R1 minus R2 over R1 minus R2 cubed. And this factor, which we call the electric field, is a vector field that fills the entire space. Now one can say, is this just a trick to make us feel better, that this charge Q1 emits this field that fills all of space, and charge Q2 finds itself in this field and therefore feels a force? Well, it's invisible, colorless, odorless, and so we can say this is just a technique to make us feel better and not have to worry so much about what is called action at a distance or action across this vacuum. The field is basically the force, since we can always we can do this factoring and take the charge Q2 and factor it, divide it into F. We can see that the electric field in general is always the force per unit charge, or the force divided by the charge that experiences at that point. So at any point, if we want to find out what the electric field is at any point in space, we simply put a unit positive charge at that point and determine both the magnitude and the direction of the electric field. In a certain sense, the concept of the field takes the magic out of the action across the distance through a vacuum. But you would be certainly correct in saying this is just a simple factoring. The question then becomes, is the electric field a fictitious device that's just a mathematical trick, or is the electric field something that's real? We will answer this later when we actually show that if we take a particle and shake it, we take one of these charges, like pretend that Q1 is not here, and we take Q2 is not here, we take Q1 and we shake it, and then we make it disappear. We neutralize it with some other charge that's equal and opposite. That oscillation should in fact continue over here and later on make Q2 oscillate even though Q1 is no longer present. That does happen, and we do find that the electric field is something that physically exists, and we will derive the properties of that field and find that it corresponds to a very interesting phenomena that's very different from ordinary matter, namely a photon, a particle that travels at the speed of light that constitutes the electromagnetic field and which has no charge and no mass. Again, continuing our rapid review of classical mechanics, let's look at the gravitational field. And we can do in the same manner. We can look at the force of particle 1 on particle 2, which is identical in form, except that we have brought the mass m2 out front. We don't have the negative sign that we had before. The gravitational constant g replaces the constant k. But the form, the vector form, is identical as before. By taking that and factoring it out, we end up with m2 times g, which looks like, in fact, the old freshman equation, force is mass times g. And that's true near the surface of the Earth, where g is the acceleration due to gravity. And of course it has the dimensions of acceleration, where it did not in the case with the electric field. But here, g is actually the gravitational field. And the gravitational field has the dimensions of acceleration, something that becomes very important when we look at general relativity. And we realize that there's an equivalence between acceleration and a gravitational field. It goes back to this fact right here, and of course the dimensionality of mass, and the fact that all masses fall at the same rate in a gravitational field. All this becomes linked together and gives us a concept with a gravitational field that's very different from the electric field. Likewise, we see that the gravitational field is the force on a unit mass, force per mass, and so anytime you want to find the gravitational field at a point, you simply take a unit mass, which as we know is 1 kilogram, place it at that point, look at the magnitude and the direction of that force in newtons, and you will have the actual gravitational field at that point. In a similar vein, one can define the magnetic field as the force on a unit north pole, although that's a little bit more ambiguous. Again, we can say, are these fields real or are they mathematical conveniences? They are real because we can introduce oscillations in these fields which carry energy and momenta. That is true of not just the electric and the magnetic fields, but also the gravitational fields.